versus NP. Okay, so N is solve, and NP is given certifier and verifier is the answer true or false. Okay, so both of these, the question is about if it's in polynomial time, right? So it sometimes means you can solve in polynomial time, and some things you can only certify in polynomial time. Like 3-SAT, you can only certify in polynomial time. There's no way to solve it with a polynomial algorithm, right? So from there, 3-SAT is a version of a satisfiability problem, and it's in what's called conjunctive normal form, which is clauses that look like this. There are ors here and ands between. So 3-SAT means that there are 3 variables. So it'll be like x1 or x2 or x3, and then it'll be and x1 or x2 or x4. Is like a really simple example. And you can tell just by looking at this, like what the answer is, and you can imagine the way that she would solve this is you'd be like, okay, x1 is true, so that makes this one true and makes this one true as well, right? But if this was a not, you make this one x1 true, well, this one's not true anymore, so then you make x2, and so you can see why it's not solvable in polynomial time, right? It would just become this like explosive thing where it's possible to be like a cubed situation, right? With like exponential growth based on the number, like how many different clauses there are in each, what the clauses are in each one, and how they connect.
So with solving also, like in order to solve it, it could potentially take up to polynomial or exponential time.
Right.
Okay.
Okay. So 3-SAT is a member of the exponential set and also NP. And so there's that picture of all the different sets. So the picture looks something like this. So
do you want to grab it up on your computer?
Oh, I
okay, you know it.
Okay, so there's like this is NP, right? And then this is P, and then there's NP complete, and then there's NP hard, right? And then like obviously all of this is part of the exponential time, right? And like all of this is part of n exponential, because n is always a superset of the normal set. So like this is what you keep in mind whenever you're trying to figure out where am I, right? So you know that 3-SAT is NP, so it has to also be an exponential time, right? Anything that's in P has to be also an NP. So like those true-false questions that Gull likes to do, if you remember this picture, it helps.
Oh my gosh.
Like I draw this picture on exams all the time, right? Because I'm too stupid to visualize it and be like, no. Right, and like the more times you draw it, the more intuitive it becomes, right? Because this one is solving and this one is checking. So if you can solve it, of course you can check it because you can just run your solver, right? And if it's NP hard, it has to be NP because the definition of NP hard is it's an NP problem that you can reduce every other NP problem to. So if it's NP complete, it has to be NP. It has to be NP. And if it's also if it's NP complete, it has to be NP hard because NP hard is any problem that you can reduce every NP problem to, but maybe it's not NP itself. Right. So there are things that can be in NP hard that aren't in NP, but there's also a big section that are in both.
So what would make something NP hard but not NP complete?
Something that itself is not NP. I don't remember. There's examples online, but I don't remember what they are.
Okay, cool.
But yeah, so basically anything itself that is not checkable in polynomial time, but you can reduce everything else that is checkable to it. And like you would never want to do that, right? You just made your solution worse. But and then there's this thing to keep in mind, right? Like the way that it's drawn out is So the way that it's drawn out is something like P in NP in exponential in NPX. So this symbol means it's a set of, but it also means at least as hard as. So P is at least as hard as NP, which is at least as hard as exponential, which is at least as hard as NP exponential, right? So there's this like chain of things. So and that matches up completely with this. So like Gall draws this on the board. Yes. She drew it in my TOC
She
class.
uses the symbols, but only for P
And
is
NP.
at least as hard as NP.
Yeah. So like this is, you might get to exponential eventually, but this is what she drew in my class, right? And then there's some that overlap, right? Like NP and like NP hard are, let me get the blue out again. Okay, so like here also, on the same level as NP is like NP hard. And on the same level of that is NP complete, right? Because all three of these are underneath exponential, but there's no subset, right? Like P is to the left of NP because it's a strict subset of NP.
Mm-hmm.
And these three are to the left of exponential because they're strict subsets of exponential. There's no way for you to determine how they relate to each other because they're at the same level of nesting.
Oh.
Yeah.
Okay. Because they're in that circle, and there's parts of it like a subset.
Yeah.
Okay.
Yep. And so if eventually you get to this point in the class, the way to remember the order is to draw this picture and then go from the inside out.
Oh my gosh.
Is how I remember how to do it.
I feel like this wraps everything with
Yeah.
NP completion.
Yeah, I feel like NP complete was one of the worst parts of the class because there's the saying it aloud part, which is hard, and then there's the understanding, which is hard, and then there's reductions, which, so from when I took algo, I had a bad 311 professor, so there was this huge gap of knowledge. Like, I never learned how to do induction over a graph, and all of a sudden I was supposed to know how to prove it. And I went to my TA and I was like, I've never done induction over a graph before. And I was like, that's why my homework looks like I've never done it before, because I haven't. And I was like, pretend that I've never done it before because I have. And like, it was just really hard to get them to understand that there was this gap that we just weren't getting, because algo is like every other class here, right? It used to be 3 and now it's 2. Or it used to be 3 and now it's 1. Because they decided we needed to graduate in 4 years, so they gave us fewer classes.
But therefore everything's like merged into one. Or you have to
And I don't know if the professors talk to each other about their syllabi, right? Because if they did, we would be learning graph induction in 311 instead of scrambling to try to catch up in algo.
Could you go over the induction too?
Yeah.
Or not induction, reduction you did earlier with the other.
Okay, I'm just going to write all this.
Yeah. We have it written down. The diagram at least. Which is like
Well, it's on the video.
the most amazing diagram because I've memorized what's NP complete.
And you've memorized the diagram already, right?
Yeah.
Because the diagram's not that big. Okay, so let's say that, I'm too sorry. I always forget that the symbols are backwards. Okay, so we have that B polynomial reduces to A, right?
So can you go over what those mean?
Yeah, okay, so this is a problem, and this is also a problem. So polynomial reduction means turn B into A in polynomial time.
Okay.
Right? So what that looks like visually is we have B, and I'm going to put it into some black box, and I'm going to turn it into A. And this black box runs in polynomial time. So that the person who originally had B, for them what happens is they put their input into this side and they get their output, right? So to them, this is also a black box, right? They give you their input and they get their answer. So I'm sure this is written this down, but now it's going to make sense, right? So it's something like A evaluates to true if and only if B evaluates to true, and A evaluates to false if and only if B evaluates to false, which means it's a valid reduction. So this happens for every valid reduction. Because if this isn't true, oh, your computer went to sleep. I don't know if that means it stopped recording.
It should still be recording.
Okay, good. So this has to be true for the reduction, right? Because if it's not and you reduce, it didn't work. Mm-hmm. So this isn't exactly the right notation, but I know that Go likes to use this kind of logic in class. Mm-hmm. But when you write this down without this, it doesn't make any sense, mm-hmm. right? It's a missing step. So this means this. You have an input for B, and you get the output, and you get the correct output by turning B into A, and then redoing the input and output.
What is that?
Black box.
No,
so this is, sorry, that arrow, this is the bad notation because I don't remember what the notation is. Mm-hmm. This is evaluates to. That's what the arrow means.
And the next symbol is on A.
That is F.
That's an F. Okay.
Yeah.
Okay.
True for. Yeah. I use the same arrow notation as you.
Yeah, I don't remember if that's what. Did you know that in Google Docs, if you do dash, it turns into the arrow symbol?
I use that all the time.
Same.
True for
I use the keyboard shortcuts in Google Drive like a crazy person, and then I go to something else and they don't work, and I go back to Google Drive.
Same. True for every valid reduction.
Yeah. So, I'm gonna wait till you guys have written down, and then I'll do the example.
Yeah, we've got written down.
I have class at 6. So
okay.
I can send you the video.
All right, thank you.
You should post it to your Piazza.
Yeah.
That is pretty serious. I posted everything I ever did to my Piazza because I was like, I have this, I should share it.
Let's send them.
Okay. So I'm going to leave this up here because we're going to use it. Mm-hmm. Okay. So the action we're going to do is that B is the 3 sat.
My charger.
And A is 3 colors. Oh, it was closed for noise because I'm doing, yeah. Okay, there you go. So the problem is 3 sat, and we're going to reduce it to 3 colored. So we're going to take a 3 sat and make it 3 colored. So let's say that our 3 sat is x1 or x2 or x3 and x4 or x5 or x6, right? So that's what we're going to start with. What we need to do is create a graph because for 3 coloring, the question is, can I color the nodes in such a way that no 2 nodes of the same color are connected, and they're basically, so like coloring a map of the United States, right? Your teacher was always like, get out 4 colors, make sure no 2 edges touch. That's because a map of the United States is not 3 colorable. If you did that, 2 color states of the same color would touch. Mm-hmm. So that's what 3 colorability is. So we're going to take this and turn it into a graph and determine if it's 3 colorable, and that will tell us if the original 3 sat is satisfiable. So the way that you do this is you basically create triangles, so like x1, x2, x3. So the nodes are the variables, and these edges indicate that here they show that they're in the same clause. And so the same for this one. And so now we have these 2 disjointed graphs that if we ran 3 coloring on, the answer is obviously yes, we can do it. So these are the variables, and this connection means in the same clause, right? So that's how we construct this graph, and this one was really obvious and really easy because our clauses were disjoint. So if they're not disjoint, the graph has to look different, right? And the way that I always did this was I created my triangles first, and then I tried to change it. So if we make this 4 a 2 instead, so this 4 becomes 2. You look at these two, and you realize, oh wait, this is the same thing. So what you do is you erase these lines and you redraw them so that they look like this. And then you run through coloring on this new graph. And for really complicated clauses, this is like super inefficient. But for an exam, it's better to do things in a way that takes like 30 extra seconds and is always right than a way that takes a short amount of time but is probably wrong.
Mm-hmm.
So that's what I always did. I always drew exactly the triangles and then erased the ones where they overlapped and redrew the lines between them. And I always did it one at a time, right? Because if there's 3 or 4 new ones, I'm going to draw the lines in the wrong place. So then you run through coloring over that. So these lines are in the same clause, and this line is same variable in 2 clauses.
Cool.
Yeah. So if you were going to try to draw this graph straight, you would just, what I would do is draw out all the nodes with labels, and then any two that are in the same clause, draw a line, and any one that's in 2 separate clauses, just draw a line there. And for some people, that works better than the triangle way. But it depends on what works best for you. I always found that if I did it the second way, I would lose track of which lines I've already drawn.
Yeah.
So I always do it the triangle way because I can get it right that way. So then, what this ends up looking like is right. So they give their input is this, and the output in this case is true, right? And so this black box here was all of this that we just did. Was going from this to this.
Wait, so the input was the green.
Yeah, so, sorry. The input is the clause.
Clause. Okay.
So, original clause. So, in this case, that proof that we wrote earlier becomes, we're going to call this black box. It becomes black box gives true if original 3-sat is satisfiable. Which again is that proof that ends up with all these weird notations and symbols that when you're looking at it and you're tired at 3 a.m. you just don't understand anymore. Right? It basically just means that the answer you get from this reduction is always right. And basically for reductions, unless you're coming up with a brand new one, most of the reductions have already been proved, and you can just look at them and get an intuition for what you should be doing, right? So in this case, if you had never seen this before, you were given a 3-sat and you had to go to 3 color. Okay, so 3-sat is, again, it's this C and F form that you know about, so you can give yourself an example like this. And you know that 3 coloring is a graph problem with nodes and edges. So what you do is you say, you ask yourself these questions. What are nodes? What are edges? What do edges mean? Right? So the answers in this case are pretty straightforward, right? Nodes are variables. Edges are connections between variables. And it means one of 2 things, right? It means either in the same clause or same variable in 2 separate clauses. So this 2 separate clauses thing, that is an example of the transitive property. Right? Because with the transitive property, it says if A is related to B and B is related to C, then A is related to C. And in our case, when I drew those original 3 little triangles, And in this case, this B when I was x4 for us in that original one, right? So so like for this set of nodes, it was that x6 was connected to x4, and x4 was connected to x1. So x4 should be connected to x1, and we can eliminate x4 in the graph because we don't need it for the three-coloring polynomial. Yeah. Okay. Any questions?
Not on this, I think.
Okay. Cool.
Thank you so much. I appreciate it.
I'm gonna leave it up there.